Hello everyone, I'm so pleased to be here to share our research. The title of this paper is Outage Probability for Device-to-Device and Cellular Heterogeneous Networks over Nakagami-m channels. The corresponding author of the paper is Zhou. We will introduce our study by 5 sections: Introduction, System Model, Outage Probability Derivation, Performance Evaluation, and Conclusion. Part 1. Introduction. Nowadays, the explosive growth of the communication devices led to an increasing demand for higher capacity, data rates, and radio spectrum resources. Device-to-device communication has been seen as a key component in the 5th generation wireless network, since it allows two adjacent D2D enabled users to directly establish communication link without base station assistance or control. Underlay D2D devices in conventional cellular networks has the potential to reduce the transmission distance, improve spectrum frequency, and offload the traffic from the base stations. It can be seen as a two-tier heterogeneous networks, where one tier is composed of the users that communicate over the D2D link, and one tier is the users transmitting signals through the base station. The shared D2D cellular heterogeneous network improved the spectrum utilization, but it also introduced the interference from both the D2D tier and cellular tier. In recent years, the performance analysis of the D2D communication in cellular networks has been extensively investigated. The outage probability is one of the key performance metrics to model the D2D communication underlying the cellular network. The outage probability analysis of the D2D cellular heterogeneous network under relay feeding channel or Nakagami-m feeding channel, by assuming the feeding parameter m was a positive integer, has been well studied in the previous literature. However, to the best of the author's knowledge, none of these previous studies considered a seminal noise, and the outage performance of D2D cellular heterogeneous network over Nakagami-m feeding channel with arbitrary feeding parameters has not been reported in the literature. In this paper, we derive an analytical expression for the outage probability of the D2D and cellular heterogeneous networks. And we assume that the typical D2D transmitter is equipped with multiple antennas. The D2D transmitters and cellular users are equipped with single omnidirectional antennas. Both the desired signal and co-channel interference experience the Nakagami-m feeding with different feeding parameter. Then the closed-form expression for the outage probability is derived for D2D links over Nakagami-m channels, which is valid both for the integer and non-integer values of the shipping parameter m. By using the outage probability as a performance metric, we investigate the impact of the system parameters on the D2D communication. Part 2. System Model. In this section, we consider a two-tier uplink heterogeneous network, where the D2D users and cellular users are randomly placed in the base station coverage area, as shown in Figure 1. D2D transmitters can directly communicate with its associated receiver without through the base station assistance. But the D2D pair is interfered by the cellular users because D2D transmitter reuse the uplink frequency band of the cellular networks. Since the element of the feeding channel vector follow the Nakagami-m distribution, the feeding power of each subchannel is considered to be the gamma distribution. The probability density function and complementary cumulative distribution function are given as follows. While Proposition 1 merely deal with the feeding scenarios of gamma distribution with integer shaping parameter, we further introduce the approximated expression for the non-integer shaping parameters. The complementary cumulative density function is derived as follows. Part 3. Outage probability derivation. The received signal at any receiving node, including the desired signal, interference from the both D2D transmitters and cellular users, and the additive white Gauss noise. Through this paper, we consider a typical D2D device which is located at the center. Denoting D and H are the distance and the channel feeding between the D2D transmitter and receiving nodes in a typical D2D pair. Thus, the received signal is derived, and the signal to interference and noise ratio, denoted as SINR, at a typical D2D receiver is derived as follows. In this paper, the outage probability is defined to be the signal to interference and noise ratios false than a predefined threshold, which is denoted as gamma. For a typical D2D receiver, the outage probability has been derived in terms of the Laplace transformation of the interference. The interference is represented in terms of a series of weighted summation of gamma random variables. Based on the second-order moment matching method, the shaping parameter beta and scale parameter lambda of the gamma distributed random variable are derived as follows. It is worth that the parameter beta and lambda are not always integer. The method of the Proposition 1 is not directly applicable. The expression for the non-integer parameter can be used for deriving the outage probability. With the shaping and scale parameters in previous presented, the Laplace transformation of the interference is denoted as follows. After some manipulations, the closed form expression of the outage probability at a typical D2D receiver is derived. Part 4. Performance evaluation. In this section, we compare the analytical results of the outage probability for a typical D2D link with the simulation results. Figure 2 shows the coverage probability of the D2D receiver with respect to signal-to-interference and noise ratio threshold in terms of different feeding parameters. We observe that the proposed expression closely matched the corresponding simulation results compared to the approximated expression proposed in reference 15. Outage probability of the D2D communication decreases as the feeding parameter increases due to the decrease in channel feeding. Figure 3 presents the outage probability with respect to the number of the antennas at the receiver side. Analytical results are very tight with the simulation results. It demonstrates that the D2D with multiple antennas assure a great outage performance improvement. Figure 4 presents the outage probability versus the average signal-to-interference and noise ratio (SINR) for different threshold gamma. We can see the average signal-to-interference and noise ratio (SINR) in general decrease the outage probability performance due to the increased desired signal. Part 5, the final part, conclusion. In this paper, outage probability for D2D links has been analyzed in the uplink D2D communication and cellular heterogeneous networks. The closed form expression for the outage probability has been derived over the Nakagami-m feeding channels. The expression is valid for both integer and non-integer values of feeding parameter m's of the Nakagami-m feeding. Analytical results are very tight with the simulation results. These results also show the impact of the number of the D2D receiver antennas, Nakagami-m feeding parameters, and average signal-to-interference and noise ratio (SINR) on outage probability performance. And the non-integer feeding parameter of the Nakagami distribution can be extended to model the kappa-mu shadow feeding and fluctuating big-man feeding channels in further studies. That's all. Thank you for listening.